So this video is to help you with the sapling homework 10 on chapter 10. I will go over question 8, 10, 11 and 12. So let's start with question 8. Again, as usual, my values may differ from the values you have because sapling generates new values for each person. So here, the question is a 37.05 gram sample of a substance is initially at 22.2 degrees Celsius. After absorbing 1,681 joules of heat, the temperature of the substance is 143.8 degrees Celsius. What is the specific heat capacity of the substance? And according to the unit given in the box here, it's S in units of joules per gram and per degree. So I've rewritten the question here in Word. So that's the values I have. Of course, your values will differ. So what do we have? We have a mass of 37.05 gram. We have a temperature initially at 22.2 degrees Celsius, and the temperature at the end is at 143.8 degrees Celsius. So Ti and Tf, so we have the temperature change. And we have Q, which is the heat of 1,681 joules. So we will need to use the heat equation that says Q equal ms delta T. M is the mass, S is the specific heat capacity, and then delta T is the temperature change, so Tf minus Ti. And we are looking for the specific heat capacity. So we will need to rearrange this equation such that we have S equal to the rest of the variables. So we solve for S, and that means you divide both sides of the equal sign by M delta T. So then it becomes S equal Q over M delta T, or delta T is Tf minus Ti. And so S, because it has M delta T multiplied to it, will be, this will cancel out if you divide by M delta T. So then S is by itself on the left here. So it looks like we have all our values in the correct units, joules for the heat, degrees Celsius for the temperatures, and grams for the mass. So we can plug in the values. So let's do that and plug in the values here. So Q is 1,681 joules. M is 37.05 grams. Tf is 140.8 degrees Celsius. I'll put the degrees Celsius on the outside. And then Ti is 22.2 degrees Celsius. So all of this is a degree Celsius. Okay, so you can see that none of the units will cancel. So we have joules per gram and per degree. And so S will keep that unit of joules per gram and per degree Celsius. So we need to do this intermediate answer here of the subtraction. It is important because it's not the same rule. It's not sig figs here. It's the least number of decimal places or the least precise digit place. And here both temperatures are given to 1 decimal place. So we will need to keep it to 1 decimal place. And the calculator answer is 121.6 in my case. So I need to know how many significant figures this becomes now, because now we are doing a multiplication and division, multiplication here, division otherwise. And so it is important to know now the number of sig figs. That's why we need to know this intermediate answer. So in the calculator, you do 1,681 divided by 37.05. and divided again by 121.6. You can also do 1681 joules divided, open the parentheses, input the mass times the temperature difference, close the parentheses. And the calculator answer in this case is 0.3731177. So this is joules on top per gram and per degree. We need to run this properly. We have 4 sig figs in the heat, 4 sig figs in the mass, 4 sig figs in the temperature. So we need to keep 4 sig figs. So we'll keep the 0.3, 7, 3, and 1. What comes after the 1 is a 1, so you keep the 1 a 1. And that's it. That's 4 sig figs. And then the unit, of course, stays the same. And it's joules per gram and per degree Celsius, which answers the question here. So let's enter that in sapling. Okay, let's go to the next question. I want to do question 10. So question 10 says the temperature of a sample of lead increased by 22.7 degrees Celsius when 250 joules of heat was applied. What is the mass of the sample in milligrams? So we want the mass of the sample of lead in milligrams. And we have the specific heat capacity for lead, silver, copper, iron, aluminum. And in my case, I have a sample of lead. So you may not have lead, you may have something else. So you need to adapt and your values may be different. So let's work this out. So I've rewritten the question here in Word. So the temperature of the sample of lead increased by 22.7 degrees Celsius when 250 joules of heat was applied. What is the mass of the sample in milligrams? So what do we have? We have delta T. This is delta T. It's not a temperature, it's a difference in temperature. It's a temperature change because it says increased by 22.7 degrees Celsius. So that's delta T here. We have Q, the 250 joules of heat applied. And we are looking for the mass. And so here, because we have a sample of lead, in my case it's lead, so I've extracted from the table here the value for lead. Lead has a specific heat capacity of 0.128 joules per gram and per degree. So you have to use the value of your sample, of your type of substance. So we are looking for the mass of lead in milligrams. So we will use the heat equation. So it's down there. The heat equation says Q equals ms delta T. But we are looking for m, the mass. So we need to rearrange such that mass, we solve for mass. And so m will be q divided by s delta t. You divide both sides of the equal sign by s delta t. And so that's m equals q over s delta t. And so we are ready to plug in the values. So let's do that. Q has a value of 250 joules. S is 0.128. And the unit is joules per gram and per degree. And then delta T is 22.7 in my case, and that's degrees Celsius. So we can see here that the joules will cancel, the degrees Celsius will cancel, and we'll be left with grams, and grams are in the denominator of the denominator, so they will move up, and so the answer will be in grams, which is a unit of mass, so that's correct. So in the calculator, you do 250 divided by 0.128 divided again by 22.7, or you do 250 divided, open the parentheses, 0.128 times 22.7, close the parentheses. And the calculator answer is 86.04 in my case, 07, etc. So we need to run this properly. And here, notice how the joules were given with only 2 sig figs, right? There is no dot after the 0. So that means 2 significant figures there, 3 significant figures in the specific heat capacity, and also 3 in the temperature change. So the limiting one is the heat with only 2 sig figs. So we need to keep 2 sig figs. So we'll keep the 8, the 6. What comes after the 6 is a 0. So you keep the 6. And that's where the dot is, and that's grams. So be careful. The question was asking for the mass in milligrams, and here that's the mass in grams. So we'll need to change the grams into milligrams. And we know that 1 milligram is 0.001 gram, right? This comes from your table of metric prefixes. So we will use this as a conversion factor, and our given amount will be 86 grams. So let's enter that here. So we have a mass of 86 grams, and we want to convert that into milligrams. So milligrams will be the desired unit on top here, and it's 1 milligram. And to cancel the grams, we have to have the grams on the bottom of the conversion factor, and that's 0.0001 gram. So you do 86 divided by 0.001, and that's 8,604. No, actually, it's not 8,000, it's 86,000. 40.7, etc. And that's milligrams. We need to run this properly. Again, we need to keep 2 sig figs because what was given was limiting to 2 sig figs because of the heat, right? We see that here. Actually, I realize now that I should not use the rounded answer there. So let me back up here and remove that and instead use the 86.0407 because that's going to be more precise. And actually my calculator still had the value, so that's still correct there for the answer. When you have an intermediate answer, you do not want to round it. You only round in the end. And here, because it's a factor of 1,000, you know, it doesn't really change the value. But when you have when you multiply or divide by other values, it's important to keep the full value and only round the final answer. That's an important concept here. So we need 2 sig figs, and here it's going to be 86,000, right? I need 2 sig figs, the 8 and the 6. Then everything after that becomes a 0 until until we would put the decimal point, but we don't show the decimal point because otherwise it would be 5 significant figures. We want only 2, and that's milligrams. So let's enter that in sapling, 86,000 milligrams. Okay, that's correct. So pay attention to your significant figures. So question 11. The specific heat capacity of a certain type of cooking oil is 1.75 joules per gram and per degree Celsius. What is the amount of heat exchanged when the temperature of 2.20 kilograms of this oil is cooled from 191 degrees to 23 degrees Celsius? So we are looking for a Q, heat in joules. So let's rewrite this in the Word document. Okay, so I have rewritten the question in Word. So the specific heat capacity of a certain type of cooking oil is 1.75 joules per gram and per degree. What is the amount of heat? So it's in joule because the answer here is expected in joules. So what is the amount of heat exchanged when the temperature of 2.20 kilogram of this oil is cooled from 191 degrees Celsius to 23 degrees Celsius? So what do we have? We have the specific heat capacity of the oil, 1.75 joules per gram and per degree Celsius. We have a mass of 2.20 kilogram of oil. We know that it's cooled from 191 degrees to 23, so that's Ti and Tf. Initial temperature is the highest temperature, and then the final temperature is 23 degrees, so it's cooled down. So you have to be careful here to keep this, in the correct order. Initial temperature is the highest one, the final is the lowest one. So we are looking for the heat exchanged in joule, when that cooking oil is cooling down. So the formula is Q equals ms delta T. Delta T is Tf minus Ti, always Tf minus Ti. So are we ready to plug in the values? Here we have mass in kilograms and specific heat capacity request per grams there, per grams per degree, and it's joules. So we have the degrees, but we don't have the grams, we have kilograms. So we will need to change the kilograms into grams. And we know 1 kilogram is equal to 1,000 grams. That's the prefix kilo here. The prefix kilo has a value of 1,000. So if we take our mass of 2.20 kilograms and we need to convert it to grams. So we start with kilograms. So the conversion factor will have the 1 kilogram on the bottom to cancel the units of kilograms. And then on top, it's going to be the grams. So it comes down to multiply 2.20 by 1,000. And that's 2,200. Okay, here we have to show that we started with 3 sig figs because in the mass here there is 3 sig figs. So let's underline the first 0 here to show that this is the last significant digit. And that's units of grams. Okay, so that changes the mass of oil from kilograms to grams. So now we are ready to plug in the values in the heat equation. So let's do that. Mass is 2,200 grams. And we have the have it underlined here to show the number of sig figs. This is multiplied by S is 1.75 and the units are joules on top per gram and per degree Celsius. Okay. And we need now to multiply by Tf minus Ti. Tf is 23 degrees Celsius. Ti is 191 degrees Celsius. So all of this is degrees Celsius here. I will put the degrees Celsius in the outside of the parentheses. So we can see that grams will cancel, degrees Celsius will cancel, and we'll be left with joules, which is the unit we expect for Q. So Q then will be equal to, And we need to calculate the intermediate answer here. So let's rewrite everything. So 23 minus 191, it's a negative 168 according to my calculator. So make sure you have your own temperatures there. So that's the intermediate answer for the temperature. So now let's calculate that. So it's 2,200 times 1.75 times negative, and so it use the negative sign in parentheses from your calculator, not the subtract sign. 168, and that's equal to Q equals negative 646,800. That's the calculator answer for my case. So we need to pay attention to significant figures, and we have 3 sig figs in the temperature, 3 sig figs in the specific heat capacity, and 3 sig figs in the mass, because we started with 3 sig figs in the kilograms. So we need to keep 3 sig figs. So we'll keep the negative 646. What comes after the 6 is an 8, so we need to round the 6 to a 7. And then we need to show that this was actually in the thousands place here. So 0, 0, 0, and then joules, right? So the 6 is rounded to a 7, and then you keep it in the thousands place. That 7 is in the thousands place. The 6 is in the 100,000s place. So 647,000 joules in my case. And that should be the answer here. So let's enter that in sapling. So negative, oh, it says not a valid number. So I guess they are not expecting negative value. Okay, well, let's enter it positive. Let's try that. Incorrect. Well, the sign is incorrect. Okay, I was trying to put it, but I guess there is a way to do it, and I'm not sure what it is. Okay, I tried again by entering negative and then the value. This time it accepted it. I guess you should not start by entering the negative sign. Start by entering your value and then put the negative sign afterwards. It accepts it this way. And you can see here, that's correct. Negative 647,000 in my case. Okay, so be careful here. If you don't show the negative sign and it should be negative, it will be counted wrong. So it can be just that makes it incorrect if you got an incorrect answer. But be careful that I advise you to put the negative sign after you've put down a value. So let's go through question 12 now. The specific heat of a certain type of metal is 0.128 joules per gram and per degree. What was the initial temperature if 0.305 kilojoules of heat is added to 76.6 grams of metal to reach a temperature of 85 degrees Celsius, 85 with a 0.0. So we are looking for an initial temperature in degrees Celsius. So let's rewrite this in Word. Okay, so I rewrote the question in Word. The specific heat of a certain type of metal is 0.128 joules per gram and per degree Celsius. And in a problem earlier, we saw that this was lead, actually. What was the initial temperature if 0.305 kilojoules of heat is added to 76.6 grams of metal to reach a temperature of 85.0 degrees Celsius? So what do we have? We have the specific heat capacity of the metal, 0.128 joules per gram and per degree. we have a Q of 0.305 kilojoules of heat added to a mass of 76.6 grams of the metal. And we are reaching a temperature, so that means it's the final temperature here to reach a temperature of 85 degrees Celsius. So that's the final temperature. And we are looking for what was the initial temperature. So we are looking for the initial temperature, and it's implied here that it actually it's expected to be in degrees Celsius from the box here in sapling. So initial temperature in degrees Celsius. So we will use the heat equation that says Q equals ms delta T. Delta T is temperature, final temperature minus initial temperature. So we are looking for Ti. So let's rewrite this so that we solve for Ti. So first, let's get rid of the times ms from the delta T. So by dividing both sides of the equation here by ms, you get rid of the ms on the side where you have the temperatures, and that's Q over ms on the left equals Tf minus Ti. We're looking for Ti, so we need to move Ti on the left side, because here on the right it has a negative sign. So let's move it to the left side, and it's going to become positive. And then the Q over ms, let's move it to the right side, and that's going to be negative in front of it. So we will have Ti equals Tf minus Q over ms. We've changed Ti from the right to the left, that's why it's become positive. And Q over ms from the left to the right, and that's why it's negative. So can we plug in the values already? So we have the temperature in degrees Celsius. However, here Q is in kilojoules, and the mass is in grams, and the specific heat is in joules per gram and per degree. So because of the specific heat capacity, we have to have joules, not kilojoules. So we need to change the kilojoules into joules first. And we know that 1 kilojoule is 1,000 joules. That's what the prefix kilo means. You change the prefix kilo by its value, and it's 1,000, and you rewrite the base unit of joules. So we will use that to do our conversion from kilojoules to joules. So the given amount we start with is 0.405 kilojoules of heat. So that's our given amount. Because we have kilojoules in the numerator here, we want to have kilojoules in the denominator of the conversion factor, and then 1,000 joules in the numerator. This way kilojoules cancel, and we are left with joules, and that's what we want. So the answer will be in joules. It comes down to multiplying 0.305 times 1,000, and that's 305 joules. Keep the same number of sig figs there. And anyway, it's an intermediate answer, you should not round. So now we have Q in joules, and everything else has the correct unit. So we can plug in the values into the equation here, this equation. So let's do that. Tf is 85.0 degrees Celsius. Q, we just calculated 305 joules. M is 76.6 grams. And then times, that's a time. S is 0.128, and that's units of joules per gram and per degree. So that's everything in there. So we need to calculate this intermediate answer here before we do the subtraction. We need to see what we have to know how many decimal places we will need to keep. So we need to calculate this part and evaluate the number, the least precise digit place. So let's rewrite this and then calculate it. So in the calculator, you do 305 divided by, open the parentheses, 76.6 times 0.128, close the parentheses, equal. And so this whole part here, about sig figs, no, I mean about units. The joules here cancel, they disappear. The grams cancel, they disappear. And we're left with degrees Celsius. So let's keep the degrees Celsius there. And all of this becomes 31.1072. Let's put the degrees Celsius after. So 31.1072 in my case. So that's the intermediate answer. Let's evaluate the number of significant figures we keep, because here we had a division and a multiplication. So it's the number of significant figures that matter. We have 3 sig figs in the joules there, 3 sig figs in the mass, and 3 sig figs in the specific heat capacity. So we need to keep 3 sig figs. So that means we will stop at the 1 there. And let's underline this to remind ourselves. We'll need to keep that. So now Ti is equal to, oops. So in the calculator, you do 85 minus 31.1072, because it's an intermediate answer that, temperature there. So you want to keep, as many sig figs as your, as many digits as your calculator gives. And so the calculator answer is this in my case. And that's degrees Celsius, right? Because it's degrees Celsius minus degrees Celsius. So we keep degrees Celsius as the unit. And we are doing a subtraction. And here what was underlined, it was 3 sig figs. And it comes down now to 1 decimal place, because when we are subtracting, we need to pay attention to the least number of decimal places or the least precise digit place. And here we have 1 decimal place, 1 decimal place. So we need to keep 1 decimal place. And so this will be rounded to 53.8 will become a 9, because it's followed by a 9. So it needs to be rounded up to a 9 here. And again, that's degrees Celsius. So that's the initial temperature of the sample of a metal here. So let's enter that into question 12 of sapling. So 53.9 degrees Celsius. The degrees are notified here. So let's check the answer. And that's correct.